Little buckets, and I don't know if you can see that very well, but the sample wheel has substrates at the bottom of buckets, and that's what the samples sit on. And some of the substrates actually were magnetic targets, so they preferentially held onto magnetic grains. Okay, next is this meteorology station and upward pointing LiDAR. LiDAR is basically a laser and a thing that measures how much light is scattered from the laser light that's being emitted upwards. So you're measuring the backscattered light. So the LiDAR measures particle scattering. The rest of the MET package measured atmospheric pressure and temperature. So Phoenix landed on Mars on May 25th, 2008 in early northern summer. The landing site was chosen to have the highest ice concentration that could be found in a reasonable landing area outside the polar cap. So this is the North Polar region, and this chart here shows water content as measured by the Odyssey gamma ray spectrometer. It's actually a neutron spectrometer that's measuring the amount of ice, or really the amount of hydrogen, that is present in the soil. And this type of instrument is only good down to about 1 meter. So what you're looking at is the amount of hydrogen in the top meter. And where the brightest colors are 100% hydrogen and the darkest, the blue colors, are 0%. So what you see is that there are these areas in this kind of circumpolar region that are high in hydrogen. The polar cap itself, of course, is also very high in hydrogen, but that's excluded as a landing area. So you're wanting to sample the circumpolar region but not beyond the polar cap. These boxes were areas that were possible landing sites that we considered. In the end, we picked the landing site D primarily because it was less rocky than the other areas, but it also had very high hydrogen concentration. So there's landing site D. So Phoenix landed May 25th of 2008. We operated it from the University of Arizona, and this is actually a picture taken in front of the building where mission operations occurred. And the PI, Peter Smith, is a very interesting and colorful guy, and he is also very interested in art. So he had an artist commissioned to do a mural on the outside of the Phoenix Operations building, and this is the mural. And this is the Phoenix team sitting in front of the mural on one of the days of operation. Okay, so what I'm going to show you now is the landed area and views from the Highrise spacecraft, which is an orbiting spacecraft, at successively higher resolutions of the landing site. And what you're seeing here is patterned ground, which as you get in closer, the patterned ground starts to resolve into actual polygons. This actually sort of looks like the surface of a basketball, but what it really is the ground is fractured into polygons. And this is the close-up view, and at least I can't, it's pretty bright here. Is there any way we can get that light down? Anyway, this is a picture of the landing site at relatively high resolution. There you go. And so you start seeing these individual polygons, and these are about 20 meters across, and within them there are even smaller polygons, which are actually accessible at the scale of the landing site. So what we have here is the work area of the arm. So here we are, there's the spacecraft sitting on the ground, and this is a color-coded elevation model of the landing site showing the polygons accessible to the arm at the landing site. So these get down to like the lander size scale, or about 1 meter in scale. And so there are polygons and troughs that were accessible by the landing site. And So the Phoenix arm went out and it started digging. It actually, the first place it dug was over here, and then it moved to the right. And one thing I should warn you of is that all the samples that were analyzed actually came from this area over here. But some of the most interesting stuff was in this area over here. So just again to point out, that's where all the samples came from. This is where the stuff that I thought was most interesting was, and that was this, you can just barely see it here, but this white material. I'll talk a little bit more about that. Okay, so two key factors go into evaluating the probability of liquid water. Observational factors and theoretical models showing that liquid water is possible. So I'm going to show you how the observations in the theory were evaluated separately. Okay, so the first line of evidence for there having been liquid water at the landing site is in fact this stuff we didn't sample, namely this white stuff. This was in a trench called Goldilocks, or Dodo Goldilocks. I can't go into the rationale behind the naming convention, but it was had to do with naming everything after a fairy tale character. So it was decided in advance that we would name everything after fairy tale characters, and everybody jumped in as soon as we got images and started coming up with names of fairy tale characters to name all these sites. And it was actually integral to the way that we did the mission operations, because before you could create a command in the software we used for commanding the spacecraft, you had to have a name for the site that you were going to do the command at. So the original idea was that we were going to sample in this location, and we were going to have the sample names be the names of Goldilocks and the Three Bears. And then we changed our minds. So we took the first sample from that location, but it was before we had dug down deep enough to find this white material. By the time we had found the white material, we had decided to sample in the center of a polygon. This was actually in a trench area. Let me back up here once. So as you can see, here's where Dodo Goldilocks is. It's actually in a trough between polygons. And the place that we had then later decided to move to was in the middle of a polygon. It was thought that that would be more representative. Okay, so this white stuff had some unusual properties. First of all, as we dug, there were little bits of it that broke off. Can we keep those lights down? Like turn them down and keep them down so that we can see the kind of stuff that's sort of difficult to see. So maybe you can see them. I can't see them. But anyway, there are little clods of white stuff in here that were seen when this trench was first dug, and then 2 days later when we imaged it again, they were gone. They were completely gone. There was no evidence of them at all. So whatever it was, sublimated, and it sublimated completely. So that was the first evidence that it was pure ice. The second evidence came from actually SSI. As I said, it's a multispectral camera, and it actually was able to look at an absorption feature of water ice. And in this white material, that absorption feature showed up. If you have any soil mixed into it, even 5% of soil mixed into the ice, you would not see that absorption feature. So that implies that this white stuff was pure ice. Well, why is that important? There is a process well known in periglacial geomorphology called the formation of ice wedge polygons. And this is the way that you get segregated ice in polar terrains on the Earth. So basically what you have is when freeze-thaw is occurring, and when ice cemented ground has these thermal stresses that are imposed on it as a result of freeze-thaw, and when these thermal stresses are relieved by cracking, and once a crack occurs, once there's thawing, water can flow down into the crack. And then later, as it gets cold again, it freezes, and the ice, of course, expands once it freezes, and that widens the crack, which then allows the next time it thaws for more water to flow further down, and that actually, over time, creates what's called segregated ice. And this is well known in periglacial terrains on the Earth. However, there's other ways that you might be able to get white or segregated, by segregated I mean pure ice, into a crack. Snow blowing along the surface can act like other materials blowing along the surface, like sand, and can fall into a crack, and therefore also give you relatively pure ice. So because we don't know which process was at work, we assign the factor for liquid water, in this case, a value of medium. The next line of evidence is that there is mineralogical evidence. Again, this is from the Thermal Evolved Gas Analyzer instrument. So this is a plot from the instrument, and so basically what you're looking at is the differences in energy, the power put in to cause a temperature to change by a certain amount. So in some cases you have a huge amount of power required to get a particular temperature change, and in other cases not so much. So by doing this you can actually see the indication that certain minerals are decomposing. And one of those appears to be calcium carbonate. So in fact, the TIGA results imply that there's 3 to 5% calcium carbonate in the soil at the Phoenix landing site. Calcium carbonate is produced by liquid water in the presence of carbon dioxide gas from the Martian atmosphere. This is actually the first time that calcium carbonate in its form of calcium carbonate has been found on the surface of Mars. It's been predicted for decades, but it's never been observed. It's actually been a big puzzle. Where is it? It is, however, true that carbonate has been detected in Martian dust at about the same amount, weight percent, of about 3 to 5%. It has also just very recently been diagnosed by the Mars Exploration Rover in a specific rock outcrop. But in both those cases, it wasn't calcium carbonate, it was magnesium carbonate. So there is some uncertainty of whether this calcium carbonate is locally derived versus it's in the global dust, although it does seem to be a different form of carbonate that's been observed in the dust. But again, because of the uncertainty, we give it a value of medium. The next line of evidence comes from microscopic imaging. And this is evidence, there's some evidence from the microscopic imaging that there's been liquid alteration of some of the grains. Now again, these are tiny little grains, 50 micron, 20 micron size grains, but we find that there's a population of knobbly grains found in some of these optical microscope images. And by knobbly, I mean the grains have little reentrants, little bubbly looking things on them that suggest there's solutional removal of one or more soluble components. Now this is something we have fairly high confidence of, we meaning myself and John Marshall, the microscopists who have looked at these, but other people were less convinced and actually thought they looked more like vesicular grains. And so we can't entirely rule out that explanation, and therefore, again, we assigned this value to medium. Okay, so next we go to the probability that liquid water is possible. And again, here it's not just an individual thing. You have to take into account multiple factors that have to be present simultaneously. So those factors are that their climate models show that liquid water is possible, meaning that the temperature and pressure are above the triple point conditions for liquid water. That there's an emplacement mechanism for water, such